Okay, ladies and gents, so those of you who have joined us for the class would have gone on a mini investigation into the physical properties of 4 different metals and whether or not we could use them to build a plane. Now, in your research, did you come across this word called alloy? Did anyone of you come across a word that said alloy?
Yeah.
Does anyone know what an alloy is?
Mix of metals.
All right, one at a time, hands up. Yeah, great.
An alloy is different metals with other metal particles in them.
Yeah.
Stronger.
All right, they are made stronger with different particles in them. Sometimes it might be carbon, sometimes it's other metals. So, alloys sometimes have different sized atoms in them. You've got your pure metal and then you pepper it with different sized atoms. And what they'll actually end up doing is locking those layers in place. You know how when you hit, right, you hit the metal sheet and it will bend? Well, this prevents that from happening because there's something stopping that. All right, where before you could bend the wire and mold it because of that, you know, the lattice and the delocalized electrons balancing everything out, well, this creates points that you cannot alter or move. They are rigid and they are locked. This makes the alloy stronger. It's still relatively malleable, but it retains strength and shape. Examples that most of you will come across include brass, all right, which is 60% copper and about 40% zinc. That's what brass is, those two metals combined. Bronze is 80% copper and then 20% tin is thrown in there. Okay, so if you ever get a bronze medal, you're getting copper and tin, all right? That's why it's the 3rd place medal. It's the worst of the medals. If you don't get a medal, well done for trying, I guess. The reason why silver and gold don't react very easily. Gold doesn't react at all. Silver takes ages to react with oxygen. That's why they're the precious metals. That's why your 1st place is gold, 2nd place is silver, and you get a crappy alloy if you come 3rd. So, steel is the most obvious alloy and the one that you will come into contact more often. Okay, steel in your steak knives is about 99% iron, but we throw in some carbon here and there to make sure it doesn't break, so make sure it doesn't bend or break too well. It hardens it. It makes it hard and strong. So swords are made from steel. Anything structurally important is made from steel. That's the alloy of carbon and iron. Stainless steel has about 18% worth of chromium. Yeah, chromium. 18% worth of chromium, which is a metal that doesn't react very well with oxygen. So by putting the chromium in, you prevent your steel from rusting. Said brass, what else we got down there? If you're soldering something, has anyone ever soldered something with a metal? Yep. You use lead and tin to solder circuit boards. So, the 6th physical property. So we looked at alloys and their strength. An alloy will enhance the strength. The 6th property I want to look at is luster. What does luster mean? Shiny. Yes. It's very shiny. Metals are very shiny. And again, it comes down to those electrons that are just floating around. Okay? The electrons are only very loosely held to those metals. That's why the taste of metal. Have you ever tasted metal? Right? It feels kind of tangy. It's because the electrons are reacting with your receptors in your body. Okay? Who's ever got a piece of nail file to their... anyone ever done that to their filling? They got an electric shock? Short circuit their own nerves? I did that when I was a kid. Yeah, you know that probably don't remember those furry friends, the little chocolate bars, and they had alfoil. And then as a kid, I was like, oh, this is nice to chew on. I had fill-ins when I was a kid, and I ended up conducting an electrical potential that set off all the nerves in my jaw. So I was like, oh, what was that? So basically, I short-circuited the nerve because I had metal in the tooth that was connected to the flesh, and then I put the alfoil on. Anyway, what are we talking about? Luster. All right, so a photon of light can excite the electron. Just makes it, you know how when you excite an atom by heating it up? Well, electrons get excited when you hit it with light. And they bounce into another shell. They bounce into another orbital. A higher level. So, who remembers doing flame tests? In year 8, maybe transition day? You coat a pop stick in a metal salt and you light it up and there's different colors.
Oh no, we did the one where you had to make AFL colours out of the... Like, we did different chemicals together and...
I don't even remember my transition.
Yeah, we did that.
Well, anyway, flame tests and fireworks work on this principle. You excite them with heat or light, and what happens is the electrons will bounce up into another shell for a bit, and the moment it comes crashing back down, it transfers that energy as another wave of light specific to the shell's energy level. All right? And then, so once it comes down back into its original shell, it'll let off another wave of light and reflect it back. So that's why metals are reflective. The electrons bounce up, they come back down and reflect the light back at you. All right? Silver is great for this because you can silver a piece of glass and then it reflects all the light back to you, and then you can see yourself in the mirror. That's how mirrors work. It's just all light reflected back because those electrons are pushing it back at you.
All matter wants to go back to a lesser energy level or something?
Sorry? Yes, that's called entropy. So all matter wants to return to its original state because it's excited. Energy's been put into it. It's not stable out there. It wants to come back down to what's called a ground state. Its original stable configuration. Because as soon as you do that, the magnetics are all gone awry. As soon as you change that potential, it wants to come back down.
Is that kind of like the Big Bang about how we're still like the next T and we're still separate?
Yeah. Well, entropy is the settlement, basically.
Yeah, so...
It's the point at which everything stops.
Yeah,
So we're heading towards that.
Yeah, so it was like the Big Bang was like... And then like...
Yeah, the Big Bang was the energy exciting everything, and we're moving towards order.
Kind of like when you had in a cup of water.
Maybe,
Yeah.
in a way. Sorry, people still writing that? No?
I reckon we'll figure out how to...
So, let's start looking at reactions. Because that is another thing we need to think about when we're using metals. And different metals have different reactivities with other compounds. In order to determine the reactivity of a series of metals, you can test them with the following. You can use water, whether it be cold or hot. You can use steam. We won't do that at school. It's quite dangerous to react metal with steam.
Might blow a hole in another bucket.
Won't blow a hole in the bucket. Acids are also great for determining metal reactivities.
How do you react it with steam? Like, how do you do it?
You atomize the metal into a powder, and then you pressurize it through into a pressurized canister with steam. So what happens is you maximize the surface area. So every atom, or every molecule has a chance to combine instantly, and that releases a lot of energy in a short space of time. So acids, you can use cold dilute, hot dilute, cold concentrated, and if you're really having it time trying to react it, you can use hot concentrated. And sometimes you can use non-metals, oxygen. All right, the simple act of setting the metal on fire is enough to determine its reactivity sometimes. Gold will not react with oxygen. Copper will, over time. Magnesium does it like that, with a flash of light. Okay? And that's where we're heading, to look into these reactivities and these reactions of metals, because that's going to lead into ionic bonding. I'm going to leave that there for now. These videos, again, I'll post up so you can all have a look. Yeah, all right, I'll call it there.